All right, ready? We're going to talk about heating curves. So a heating curve is endothermic. Energy is being absorbed. Okay, we're going to skip past the video. Okay, so let's look at a heating curve. Here we go. You can tell that energy is being added because the temperature, which is over here, is increasing over time. You also can see parts where the graph is flat. You can see parts where the graph is slanted, showing temperature increase. This part is represents a solid, so between A and B. Between B and C, we have a solid going to a liquid, or melting, or fusion. From C to D, we have a liquid warming up. From D to E, we have a liquid turning to a gas, boiling. And then from E to F, we have a gas heating up. So the heating curve for water, you can see, how would we know? Well, look right here. See this temperature? This right here, 0 degrees. You must know that. That is the freezing point of water. Right here, 100 degrees Celsius. That is the boiling point for water. You must know that, okay? But what is important also noted here is this is a temperature change. So solid warming up, a phase change, melting, a temperature change, liquid warming up, a phase change, boiling, evaporation, vaporization, a temperature change, the gas warming up. All right. Again, like I said, you can find the melting point and boiling point by looking for the flat sections, the horizontal sections, and go across. This is in Fahrenheit, which we'll rarely see, so you don't need to remember these numbers. But you go across from where it is melting, and that would be the melting point. Go across from where it would be changing from a liquid to a gas, and that will tell you the boiling point. So other things that we can talk about, the heat of fusion represents how much heat is being added while it's melting. The heat of vaporization represents how much heat is being added while it's vaporizing. And what can you tell from this graph? Well, look at this. Heat of fusion is from here to here, from B to C. From D to E is the heat of vaporization. Well, that takes more energy. So the heat of vaporization would be greater than the heat of fusion. How can I tell? The length of the line. Okay, because if I'm adding a consistent amount of heat, it takes less time to melt it than it does to boil it, which means I need to add more heat to vaporize than I do for fusion. All right, temperature, remember, is average kinetic energy. So when the temperature changes, the kinetic energy changes. So the kinetic energy is increasing because the temperature is increasing from A to B. From C to D, the temperature is increasing, so kinetic energy is increasing. From E to F, the kinetic energy is increasing, so the temperature is also increasing. Now, if the temperature is constant, the kinetic energy is constant. So the kinetic energy is constant when there's no temperature change. Kinetic energy is constant when there's no temperature change. What about potential energy? That's stored energy. If the temperature is changing, the kinetic energy is changing, and the potential energy is not. The potential energy is constant. So here's what's important to remember. Either the potential energy is changing or the kinetic. So if the kinetic is changing, potential is constant. So the potential energy is constant here where the temperature is changing. Potential energy is constant here where the temperature is changing. And the potential energy is constant here where the temperature is changing. So remember, if kinetic is changing, that means temperature is changing. Potential energy is not. And then if the temperature is constant, the kinetic energy is constant. And this time the potential energy is changing. So we have the potential energy increasing when the temperature is constant. The potential energy is increasing when the temperature is constant. So those particles in that solid are melting. So their potential to be moving is greater. As those particles are vaporizing or evaporating, the potential to be moving is increasing, even though the temperature is constant. All right, so here you can see we have a solid warming up, melting, liquid warming up, vaporizing, gas warming up. And you can see from this visual, potential energy is low here, but as we move along, the potential is increasing, and so is the kinetic in general as the graph continues. So the general trend, no matter what, in a heating curve is increasing. So the potential energy is increasing, the kinetic is increasing. Not in every section, but the general trend is increasing. So let's review. How can I tell this is a heating curve of water? What do? I look for the boiling point and the melting point. If the boiling point is 100, where this long flat line is, and the melting point is 0, bam, water. Melting points and boiling points can identify substances. That's why there's a whole table S. So that's why there's this. Got my handy dandy reference table right here. So that's why there's this whole thing, this whole column for melting points and boiling points. Melting points and boiling points can be used to identify substances. And what if you forget? Well, there's one clue that this reference table can provide you for water, and that is in table H. Okay, so in table H, this line right here represents normal boiling point. So if you forget the normal boiling point of water, you can go across this line right here until you hit the graph for water, which is the third line, and go down, and then you will see that the normal boiling point of water is 100. So that one you can look up. Freezing point, no. But again, melting points and boiling points identify substances. So each substance has a unique heating curve. How can I tell this is not a heating curve of water? Well, let's see, where it's flat for melting, well, -60, and where it's flat for boiling, 60, that is not water. It is supposed to be 0 and 100. All right, so again to review, in A, we have kinetic energy increasing, potential energy constant. Then we hit the melting point, and we have kinetic energy constant, potential energy increasing during B. Then we are 100% a liquid. Now in C, all liquid, the liquid is warming up. Kinetic energy is increasing, potential energy is staying constant. Then we hit the boiling point and the liquid begins to change to a gas. And during D, the liquid is changing to a gas, no temperature change, kinetic energy is constant, and potential energy is increasing. Then finally, all of the liquid is converted to a gas, and in E, we have kinetic energy increasing and potential energy staying the same as the gas is warming up. So a substance begins to melt. What happens to the potential and the kinetic energy? The potential increases, but the kinetic stays the same. Because remember, when it melts, the temperature doesn't change. The temperature of a substance refers to what type of energy? Kinetic energy, a measure of average kinetic energy. How does the speed of and space between water molecules compare in a liquid versus in a gas? Well, molecules move faster and spread out more in the gas phase. So molecules move slower and are less spread out closer together in a liquid. And there you have it. That's heating curves. I hope you learned something new today.